Welcome back to Linear Algebra Mastery. Let's jump into Anki. No flashcards today. All right, we got a lot to recall here. There was a lot yesterday. Let's do our best. All right, partitioning, right? Partitioning is another word for subdividing a matrix using these vertical and horizontal lines known as rules. So you can create submatrices within a matrix. What's a use case for this? Well, a use case for this is actually to find specific rows or columns of a product matrix without having to do the entire matrix multiplication, because you can get massive matrices, right? All right. Another way to think about multiplying matrices is basically this thing called linear combinations. Linear combinations, I think that's what it was called, is where you take a whole bunch of matrices that are the same size and multiply each of them by a different scalar known as coefficients, and then you add them all together. They don't all have to be different, but they can be. They can all be the same scalar as well, but this is another way to think about multiplication, multiplying matrices, okay? And partitioning, linear combinations, what else do we got? Surely there's more than this. The person who came up with matrix multiplication was named Eisenstein. He was German, student of Gauss. He came up with this as a way to simplify substitution in linear systems. I don't really know what that means. We'll find out, though, as we continue to get more knowledgeable. Seeley, I believe, is a guy who continued to add to and develop matrix multiplication after Eisenstein. Linear combinations, okay. Eisenstein, cool. Partitioning, cool. Submatrix, partition matrix. Oh wow, we got everything. I thought we had a lot more, but the other thing was, the one thing we missed was the row column rule, which is basically the abstract way, the universal way to find the numerical value of an entry of the product matrix. Basically, you have the resulting matrix, an entry at a resulting matrix. The way to find this, right, so you got parenthesis, resulting matrix sub ij, so these are the location, this is the entry, and the way you find this is that equals the entry of A, matrix A at row I, column 1, times entry at matrix B at row 1, column J, dot, dot, dot. Instead of ones on the last one, we're going to do twos, dot, 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 all the way up to the last, whatever, R as the unknown. Infinite variable. Okay. That's it, I guess. We're caught up now. All right. Let's continue then. I'll be back to recall in a bit. All right, guys. Lots again here. All right. Partitioning. Okay, we learned another way to think about / solve matrices. Before that, there's a theorem basically saying if you have a matrix and a column vector, then you can take a column from the matrix and then add up, take the column from the column vector and use those values as coefficients, and then add them all up. So you coefficient, the first coefficient times it by the column from the matrix, and then the second entry from the vector column vector, and times that by the column of the matrix. You add them all up, then you will get the column of the resulting vector. What column? I'm not exactly sure. Oh, it can just be expressed. Oh, column. Okay, so the answer can be expressed as a linear combination of the column vectors of the matrix. So this is not okay. You got a matrix and you got a column vector. If you split up this matrix into its column vectors, and then you use the coefficients of the column vector, and then add all these coefficients multiply coefficients times the column vectors in the matrix, add them all up, that's the answer. So that's just how you can express the answer of a matrix multiplication. Okay, then we learned about another way to think about / solve matrix multiplication. Dang it, there's a term for this. Some term. And that one's a little vague. I'm forgetting it now. Anyway, we'll continue. The next section was the 5 ways we learned about how to multiply matrices in this chapter by definition, which is like entry by entry. So entry by entry, then row column method. This is where you're multiplying the rows by the columns. Row by row, this is partitioning. Similar to that theorem we just talked about, column by column. Again, just another way of doing partitioning. And then there's a 5th method. Dang it, 5th method, what were you? Would it be about partitioning? I don't know. We'll come back to it. And then we learned about a new way to augment linear systems, and this is, so you take, you augment it normally as we would, but you keep the variables in it this time. So you have the x's, the unknowns, and the constant in there, not just the coefficients. Okay, and then you draw a line between the left side and the right side, so you got all constants on one side of the line and the others. And then you basically state that, I know that's the first step, right? You can state that, you can actually take that where you divided and split it into 2 submatrices and set them equal to each other. So now you got like you got the constants and the variables equals the constants. The coefficient of the variables equals the constants. And then you actually you take the variables out of the coefficient and variable one, and you reorder the coefficients so that the rows, everything in the rows are all added together, and then they're multiplied by the corresponding coefficient, and set that equal to b. And then, yeah, that's how you can write, you can augment the linear system in a matrix. It's ultimately a x equals b, where b is the column vector of the constants from the original equations, x is a column vector of the unknowns, and then a is a matrix of the coefficients of the unknowns. Okay. Column row expansion was the other way. What do you do here again? Column vectors of A. Okay. So column row expansion, you basically, this is how you do it. You got a matrix, you got two matrices you're going to multiply together. On the first matrix, you split it all up into row vectors. And then the second matrix, you split all the first vector. Okay, restarting. Column row expansion. You take the first matrix, you split it into row vectors. You take the second matrix, you split it into column vectors. And then basically you can write the resulting matrix as the sum of row vector 1 times column vector 1 plus row vector 2 times column vector 2, ... all the way to however many you got of each. So that should be it for today. Yeah, it's pretty abstract, but we're doing well at grasping some of the underlying principles, concepts. Anyway, we got basically a page and a half left. Let's say a way to augment linear systems with unknowns included. Okay, because the first time we learned how to augment matrices, we got rid of the unknowns essentially. Okay, now the last section is going to be transpose of a matrix, transpose, and then trace of a matrix. So we got transpose and trace left. And then we got the problem set for 1.3. So that's it for today. Talk to you guys later. See ya.